Hey everyone, in this lecture we're going to make a brief introduction to propositional logic. In the previous lecture we looked over the two components of a logic. Each logic is the union of a syntax and the semantics. So let us study these two components from the point of view of propositional logic. In propositional logic, the vocabulary is a set of propositional or predicate symbols P, whose elements we will normally write as P, Q, R, and more. And we define a propositional logic formula on the set of predicate symbols P in the following way. And this is very important. First of all, every predicate symbol of P is a formula. So if we have P, if we have this predicate symbol, this is a formula. In the same way, if we have the predicate symbol Q, this is also a formula because it is a predicate symbol of the set of predicate symbols P. So every predicate symbol of P is a formula. The next consideration is if F and G are formulas, then the conjunction of them and the disjunction of them are also formulas. The symbol that we see in blue is called the logical AND. This operation is known as conjunction, and so when we do the conjunction of two formulas F and G, the resulting formula is true only if both F and G are true. We then have the disjunction operation. The symbol that we see in blue now is called the logical OR, and it represents the disjunction operation. And so this resulting formula is true if at least one of F or G is true. We are going to talk more about truth values later. The next aspect of a propositional logic formula is if F is a formula, then the negation of F is also a formula. This symbol that we see in blue is called the negation or also the logical NOT. And what this operation does is inverts the truth value of the formula. So if the formula F is true, then the negation of F is false. And in the same way, if the formula F is false, then the negation of F is true. And finally, given these three considerations, the last consideration is nothing else is a formula. So this statement concludes by asserting that nothing else except for what has been described qualifies as a formula within this system of propositional logic. This means that a valid formula in propositional logic can only be a propositional symbol by itself, the conjunction or the disjunction of two formulas, or the negation of a formula. Very well, let us now study the semantics component in propositional logic. We begin with the definition of interpretation. An interpretation I on the vocabulary P is a function that maps for each predicate symbol, that is, for each element that belongs to the set P, a value that is either 0 or 1. So essentially it is a function that for each predicate symbol, it tells us whether it is true or false, that is 1 or 0 respectively. So notice that in this logic, the possible values for the predicate symbols are Boolean values. A predicate symbol is either true or false. Let us now define the concept of satisfaction. So given an interpretation I and a formula F, both over the vocabulary P, then the evaluation in the interpretation I of the formula F is denoted in this way, eval, and then we have the subindex I for this formula F. This is a function that for each formula gives us a value of 0 or 1. So essentially, in propositional logic, a formula is satisfied under a given interpretation if it evaluates to true according to the truth values assigned to its propositional variables, and also the meanings of the logical connectives. We are going to see some examples later that will make this concept clear, but let us begin with the definition. We define the evaluation function for all possible cases of the formula F using the minimum, maximum, and denoting these operations together with the subtraction over the numbers from the set 0 and 1, where the following takes place. First of all, if the formula f is basically a symbol p of the set of propositional symbols p, then of course the evaluation of this formula f in this interpretation I is going to be equal to the interpretation of this propositional symbol p. And this is something that is obvious, right? If my formula f consists of basically the predicate symbol p, and suppose that my interpretation for this predicate symbol p is equal to 1, so it is true, then when we evaluate this formula f on this interpretation I, since this formula is simply the predicate p, then the evaluation is going to be basically the value of the interpretation for this propositional symbol, which we know is equal to 1. So the evaluation is also going to be 1. Now remember that we defined what was a formula? A formula in propositional logic was either a predicate symbol. A formula can also be the conjunction of two formulas. It can also be the disjunction of two formulas, or the negation of another formula. So we also need to define how we can evaluate these formulas that are not that simple, that are not just a predicate symbol. And so the definition is the following. When we evaluate a conjunction of two formulas, this is equal by definition as the minimum of evaluating each formula in the interpretation I separately. That is, we evaluate one formula and then the other, and then we compute the minimum. And the reason we compute the minimum is by definition of the conjunction operation and the truth table of the logical AND. As we mentioned, when we have the AND of two formulas, then the resulting formula is true only if both formulas are true. So remember that 0 stands for false and 1 stands for true. As we can see, if both formulas here are false, then the resulting formula of the conjunction is false. In the same way, if one is false and the other is true, like here and also here, the resulting formula is going to be false. And finally, the only case that we get that the resulting formula is true is when both formulas f and g are true. And what is this truth table? Well, this is precisely the function minimum between these two formulas, right? If we compute the minimum of 0 and 0, this gives us 0. If we compute the minimum between 0 and 1, this gives us 0. The minimum between 1 and 0, this also gives us 0. And finally, the minimum between 1 and 1, we can see that it is 1. That is why when we compute the minimum between both evaluations, we are essentially evaluating this conjunction. Remember that a formula can also be the disjunction of two formulas. So in order to evaluate a disjunction, it is very simple. We just compute the maximum, and now we compute the maximum by definition of the disjunction operation. Remember, as we discussed, the disjunction of two formulas, f, g, is a formula that is true if at least one of f or g is true. And so the disjunction can be visualized in this truth table. Notice how here we have the logical OR that represents the disjunction. And so notice, as we mentioned, if at least one formula is true, then the disjunction is going to be true. For instance, in this case, neither f nor g is true. They are both false, so the disjunction is also false. On this case, since at least one of them is true, the result is true. Here again, at least one is true, the result is true. Notice here that now what happens? Well, both are true. Well, does it happen that at least one is true? Well, of course it does. Of course it does. In fact, both of them are, but it happens that at least one is true. So the result is also true. And so, if we ask again, what is this truth table? What is this? Well, this is precisely the function maximum between the evaluation of these two formulas, f and g. If we compute the maximum of 0 and 0, the maximum is 0, the maximum between 0 and 1 is 1, the maximum between 1 and 0 is 1, and the maximum between 1 and 1 is 1. And so this is the reason that to evaluate at this junction, we compute the maximum between both evaluations. Finally, a formula can also be the negation of another formula. So to define the evaluation of the negation, it is very simple, because since evaluations are functions that return booleans, either 0 or 1, either false or true, to evaluate the negation of a formula, we just need to compute 1 minus the evaluation of the formula f without negating. And the reason we have this computation is again by definition of the truth table of the negation. As we discussed before, in the negation, what we do is we invert the truth value of a given formula f. So if the formula f is false, if it is 0, then we negate and we have 1, we have true. In the same way, if the formula f was 1, if it was true after the negation, we have false, we have 0. And what is this? What is this truth table? Well, if we look closely, this column, the negation, is precisely 1 minus the evaluation of the original formula. Notice here, if the evaluation of the formula f is 0, 1 minus 0 gives us 1. And in this case, if the evaluation of the formula f is 1, 1 minus 1 gives us 0. And this is the reason that we have this computation to evaluate the negation of a formula. Very well, let us end this introduction to propositional logic lecture with some comments on satisfaction, and that is if the evaluation in the interpretation I of the formula f is true, that is, if it is equal to 1, then we say that this interpretation I satisfies the formula f, and we denote it with this notation in here, with this vertical bar and this equal, with this pipe and this equal. This means that I, the interpretation I, satisfies the formula f, and commonly it is also said that the formula f is true in the interpretation I, or that the interpretation I is a model of the formula f. Very well, with this we end this brief introduction to propositional logic. We remind the student as always that you can download all of the documentation in the downloadable documents of this lecture.